going to talk about inconsistent and dependent systems. A system of equation can just be one of those two. Most are neither. If you have a matrix, an augmented matrix, and you reduce it, now, let's suppose this matrix is in RREF form. And let's just suppose we get 1, 0, 0, 3, 0, 1, 0, 2, 0, 0, 1, 4, and maybe 0, 0, 0. The variables are x, y, and z. The first equation, or the first row, says x equals 3. The next row says y equals 2. The third row says z equals 0. And for the record, 0x plus 0y plus 0z, this is the last row, equals 0. And 0 times x is 0, 0 times y is 0, 0 times z is 0. And here, 0 plus 0 plus 0 equals 0. That is, the last row didn't say anything. It said 0 equals 0. Okay. Now, I haven't mentioned this yet. I probably should have mentioned it before. First, let's try for the third time to erase this. Okay. What I want to say is, first of all, make believe this is true. If you have 1, 2, 3, 4, 2, 1, 3, 8, 1, 4, 2, 9. The solution to this is the same as the solution to an equivalent matrix, a row equivalent matrix. They have the same solutions. Okay? They have the same exact solutions. So let's talk about independent. If you ever have something like this, 1x plus no y plus no z is equal to 7, well, that makes a lot of sense. X equals 7. It's an intelligent statement. If the next one is 0x's plus 1y plus no z's is equal to 3, that means y equals 3. If the last row were to say 0x's plus 0y's plus 0z's, which is 0, equals not 0, like equals 8, there's no solution. There's no solution. It is inconsistent. The system of equations is inconsistent. You can have a row of zeros before the bar, before the line, and then a non-zero number on the other side. That's how you know a system of equation is inconsistent. You get a row of zeros on the left side, but on the right side of the line, you have a number other than 0. For example, if you have 1, 2, 0, 4, 0, 3, 1, 8, and 1, 5, 1, 12. Suppose you have this, and you want to solve this system of equation. That is, you want to solve x plus 2y equals 4, 3y plus z equals 8, x plus 5y plus z equals 12. You want to solve that. Now, you can use Gauss-Jordan elimination technique. You can use Gaussian elimination, which requires you to do back substitution, whatever you like. Now, in either case, in the first row, first column, we have a non-zero entry, and I want to get what's below it to be all zeros. I lucked out with that being a 0. And since this is a 1 and this is the 1, I'll just do row 3 minus row 1. The first row doesn't change. The second row does not change. The third row, 1 minus 1 is 0. 5 minus 2 is 3. 1 minus 0, 1. 12 minus 4 is 8. Okay, how about we do Gaussian elimination? So the first column is okay. Because here's in row 1, there's my leading 0. This one's a leading 0. And everything, leading 1. And everything else beneath it is 0. Row 2, here is my leading non-zero entry. And I want to get what's below it to be 0. Well, since this is 3, well, 3 minus 3 is 0. They're both 3's. So why don't we just do row 3 minus row 2? And if you notice, the two rows, row 2 and row 3, are exactly the same. And when you subtract the exact same numbers, you get 0. How about we make this number 42? Let's make this number 42. 42. Sorry about that. Well, the numbers to the left of the line, they're exactly the same. So row 1 does not change. Row 2 does not change. And 0 minus 0 is 0. 3 minus 3 is 0. 1 minus 1 is 0. But there's a minor problem here. 42 minus 8 is not 0. It's 34. This is inconsistent. There is no solution. Because 0 times x, regardless of what number x is, 0 times x is 0. No matter what value y is, 0 times y is 0. No matter what value z is, 0 times 0 times z is 0. You add up those 3 zeros, you get 0. It doesn't equal 4. There is 34. It is inconsistent. No solution. If you get a row of zeros to the left of the line, but to the right of the line, you have something other than 0, no solution. The system is inconsistent. If you had 2 lines, 2 equations, and 2 unknowns, those are lines. The lines would be parallel, but they don't meet. I'm not going to talk about planes not intersecting anywhere. It's a bit advanced, but think about what a plane is. Think about 3 walls in your house that don't intersect. Opposite walls, in most houses, they don't intersect. Let's try another one. If you have 1, 0, 1, 2, 0, 1, 1, 3, and you have 1, 2, 3, 9. Suppose you have this. Okay, here is our entry, and we want to clean up column 1. I want this entry and this entry to be 0. Well, it's pretty nice because this entry is 0. And that's a 1. 1 minus 1 is 0. That is, I'm just going to do row 3 minus row 2. The first row doesn't change. The second row doesn't change. The third row, 1 minus 1 is 0. 2 minus 0, 2. 3 minus 1, 2. 9 minus 2, 7. Okay. Second row, we're going to deal with that entry. I want to get what's above and below to be 0. Well, what's above is 0. And if we're using Gaussian elimination, it doesn't matter. This is a 2. This is a 1. If you leave row 3 alone, you'll have a 2 here. You have to double row 1. When you double 1, you get a 2. This is a 2. That will be a 2 after you double it. Subtract. 2 minus 2, 0. Okay, so let's see. Row 1 is not changing. Row 2 is not changing. Row 3 is. We take row 3, which is right now 0, 2, 2, 7, and we take away 2 row 2s. Sorry about that. We are using this row because of that 1. And take away 2 row 2s. 2 times 0, 2 times 1, 2 times 2, 2 times 3. And when we subtract, we will get the new row 3. 0 take away 0, 2 take away 2, 2 take away 2. Those are all zeros. 7 minus 6 is not 0. It's 1. It's 1. This makes no sense. If you have a row with zeros, whether it's on the bottom or not, and let me say it again, to the left of this line, if you have a row with zeros, and to the right, you do not have a 0, to the right of the line, that is, you do not have a 0, you say, no solution. It's inconsistent. It's inconsistent. If you get a row with zeros to the left of the line, and you get a row with, and you don't get a 0 to the right of the line, you get a 1 or a 7 or negative 2/3, or believe it or not, the number pi, it's inconsistent. You have to have a 0 here for it to be not inconsistent. Okay. If any row to the left of the line has all zeros, but to the right of the line, it has a number other than 0, 0.8, the square root of 13, it's inconsistent. Now, we're going to talk about dependent. When is it going to be dependent? When is this system of equations dependent? Now that one is just a little bit more tricky. That's a little bit more tricky. Okay, so why don't we state it in words and then we'll talk about it. That is, solve some problems. A system of equations is said to be dependent if after getting the augmented matrix in reduced row echelon form, you have less non-zero rows than the number of variables. If an equation has 3 variables, okay, if the system of equation has 3 variables, and you have less than 3 rows so if you have a row with zeros, or 2 rows of zeros or 3 rows of zeros, don't count them. If the number of rows that are left over, say 2, is less than the number of variables, let me be very clear, after getting it into RREF form, not counting the rows that have nothing but zeros. If the number of remaining rows is less than the number of variables, we say it's dependent. If the number of rows after get into row reduced echelon form and remove the rows of zeros, the rows that have nothing but zeros, if the remaining rows, after you count the remaining rows, if it's less than the number of variables, it is dependent. In a dependent system, you can solve. You can actually get an answer. In fact, we're going to get infinitely many answers. We're going to get an infinite number of answers. And that's why it becomes tricky. Suppose you have x plus 2y is equal to 3, and 2x plus 4y is equal to 6. Start off with a simple one. First thing you do is write the coefficient matrix. 1, 2, 2, 4, 3, 6. 1, 2, 2, 4, augmented, 3, 6. So there are 2 equations, 2 rows. If we end up with less than 2 rows that don't have zeros, well, we're in trouble. Not in trouble, it's dependent. So this is a 1. I want to get that entry beneath it to be a 0. So I'm going to take row 2, which has a 2 here. I will multiply that 1 by 2. That is, I'll take row 1, which has a 1 here. I'll multiply it by 2. That will put a 2 here. Well, if these are both 2's, when you subtract, we'll get 0. So let's do this. What is row 2 take away 2 row 1's? Well, row 2 is 2, 4, 6. And 2 times row 1 is also 2, 4, and 6. And when you subtract, 2 minus 2 is 0, 4 minus 4 is 0, 6 minus 6 is 0. Okay, so we have 1, 2, 3, 0, 0, 0. Now, just because you have a row of zeros does not mean it's dependent. Don't study it that way. That's not true. You could have no row of zeros, and it can be dependent. If you start off with 3 variables and only 2 equations, it will be dependent. Because when you reduce those 2 rows, you'll never end up with 3 rows. If you have 3 equations, you have to have 3 rows remaining in order for it to not be dependent. If you have less than 3 rows, it certainly will be dependent. Okay, this matrix is in row reduced echelon form, or reduced row echelon form. Here is our first non-zero entry. What's beneath it is 0. The next row doesn't have a leading entry, a non-zero entry. Okay, so it is in reduced or RREF form. And the variables are x and y. What you need to do is the following. Let me write this down again a little bit bigger without the writing and circles and boxes all around it. 0, 0, 0. Again, I don't care about what's to the right of the line. This is x, and this is y. Under x, it has a leading entry. It has the 1. Under y, it has no leading entry. Doesn't have neither of these two numbers is the first non-zero number in its row. The 2 is in the first row. This 2 is not the first non-zero entry. I know it isn't because there's a 1 before it and 1 is not 0. In the second row, this is not the first non-zero entry. Why? It's a 0. How can it be a non-zero entry? Whether it be the first one or the second or the third. It's not a non-zero entry. Okay. That tells us that y can be any number. Y can be r. R is any real number. Any. It can be 2. It can be negative 13. It can be the square root of 5. It can even be pi. It can be pi cubed over 3. Okay, the first equation tells us that 1x plus 2y is equal to 3. Bring the 2y over, that is solve for x. Y is equal to 3 minus 2y. But y is r. And let me just write down what y equals. Y equals r, remember? This is the answer. R can be any number. For example, what I'm about to write, let's see what they call this. A particular solution. A particular solution. Well, if I let r equal to 4, then x is 3 minus 2 times 4. 3 minus 8, or negative 5. And y is just r, which is 4. This is a solution. And you can check it. Remember that x plus twice y was supposed to be 3. If x is negative 5, and you multiply y by 2, multiply 4 by 2, negative 5 plus 8 is 3. And if you have 2x plus 4y's, you will get 6. X is negative 5. 2 times negative 5 is negative 10. Plus y is 4. 4 times 4, 16. And yes, negative 10 plus 16, more simply known as 16 minus 10, it really does equal 6. It really does. So, negative 5, x equals negative 5, y equals 4 is a particular solution. If you let x be 41, you'll get a different number probably for x. You'll get 41 for y. And you know what? If you did this, if you substitute in what x and y are, the left side will equal 3. In the second equation, you let x be negative 79 and y be 41 in here, you will get this to equal 6. Okay. But those are particular solutions. That's when that's when r is given a value. The exact answer is what remains on the board. X equals 3 minus 2r, and y equals r. And you really, really should state what r is, because otherwise it makes no sense. For any number r, you have a way of figuring out what x is and what y is. For different for different values of r, you get different x's and y's. There are an infinite number of solutions. Let us try another one. If the number, after you get it in RREF form, if the number of all zero rows is less than the number of variables, you will have a dependent system. For example, if you have this one, you have x plus 2y minus 3z is equal to 6, and you have 2x plus 4y minus 6z is equal to 12, and maybe you have negative 3x minus 6y plus 9z is equal to negative 18. If you have this system of equations, their corresponding matrix would be 1, 2, negative 3 for the first column, 2, 4, negative 6 for the second column, and negative 3, negative 6, and positive 9 for the third column. And the right-hand side will be 6, 12, negative 18. I have my non-zero entry right there. Happens to be a 1. I want to get what's below it to be 0. 1's a really friendly number because the least common multiple of 1 in any number, like 1 and 2 is 2. If I were to double, if I take row 2, the way it is, 2, and I take away 2 row 1s, 2 of those, and 2 of these and 2 of these, etc. But if I take away 2 of those, I'll have 0. 2 times 1 is 2. 2 minus 2 is 0. Now, if I keep row 3 the way it is, I have negative 3. And if I add 3 1s, if I add 3 1s, which is 3, negative 3 plus 3 is 0. So I'm going to add. And how do I get 3 1s in the first position? I multiply row 1 by 3. Okay, let us do this arithmetic. Lots of arithmetics here. Row 2 is 2, 4, negative 6, and 12. And I want to take away 2 row 1s. 2 row 1s, well, I multiply every entry in row 1 by 2. 2 times 1, 2 times 2, 2 times negative 3, 2 times 12. And I subtract. And I'm like, oh, both of these rows or numbers are the same. I'm going to get zeros. If these numbers are the same, when you subtract, you get 0. These are the same. The difference is 0. These are exactly the same. Stop changing this to addition and the sign of the second number. When you subtract two numbers, you find out the difference. You find out how much bigger one number is than the other. Well, these numbers are the same. Subtract them, you get 0. 12 minus 12 is 0. Okay, so the first row didn't change. The second row has all zeros. Now, we really would like that 0 to have been a 9. Then we can say inconsistent and move on to the next problem. But it's zeros. Let us find out what the third row should be. We do, according to our recipe here, we do row 3. We compute 3 times row 1, and we do arithmetic. That is, we add. Row 3 is these numbers. Negative 3, negative 6, 9, negative 18. 3 times row 1. 3 times 1, 3 times 2, 3 times negative 3, and 3 times 6. Now, when you add, and the numbers are the same, except for the sign, you get 0. They're the same number. 6 is positive 6, except the signs are different, and we are adding. These two numbers are called additive inverses. And when you add additive inverses, you get 0. And we're like, oh my, we have another row that consists entirely of zeros. Okay. Now, when I look at this matrix, this row, this reduced row echelon form matrix over here, I'm like, well, let me see. There are 1, 2, 3 variables. And, you can count them. 1, 2, 3. But when I count the rows that are not all zeros, there's only one of them. And that's less than 3. 1 is less than 3, which means there are going to be some free variables. It's going to be dependent. Right. Well, let me put x, y, and z. Well, under x, I have an entry that's the first non-zero entry in its row. So x is not free. But when I look at the second column, 2, 0, and another 0, none of those entries are the first non-zero entry in any row. The 2 is not the first non-zero entry in the first row because the 1 is. And the 0 couldn't possibly be the first non-zero entry in the second row. It's not a non-zero number. 0 is 0. Same argument here. So we know that y can be any number. I'm not clear why, but generally we call it r. R is any real number. Well, for the first time ever, maybe I understand why they call it r. R for real. Let's go to the third column, the one that's labeled z. None of those entries, the -3, the 0 beneath it, the 0 beneath that, none of those 3 entries is a leading non-zero entry. That means z is a free variable. And we go in alphabetical order, r and then s. S is any real number. So one nice thing about this is we already have what y and z are. Y can be any number you like, and z can be any other number. It can be the same as y. It can be different than y. Now let's go to that first equation. That first row, 1x plus 2y minus 3z is equal to 6. Let's solve for x. Equals 6. Bring their positive 2y over as negative 2y. The negative 3z over as positive 3z. X is equal to 6 minus 2y, where y is r, plus 3z, which is s. This here, I'm just copying over what I just wrote, 6 minus 2r plus 3s. This here is the solution. Y can be any number, z can be any number, and x is going to be 6 minus 2 times whatever y is, plus 3 times whatever z is. Okay, you pick what r and s can be. And when you do that, you will get a unique solution. For example, if r is 0 and if r is 0 and s is 0, then y equals r, which is 0. Z equals s times 0. Because r and s are 0. That is, x equals 6. And this here is one solution. It's the solution when r and s are 0. But you can let r be 0 and s be 22. So y would be 0, z would be 22, and x will be 6. That's going to be 0. 6 plus 3 times 22? 3 times 22 is 66. 6 plus 66 is 72. Okay, so y would be 0, s would be 22, and the x would be 72. Those are particular solutions. You pick values for the free variables. Okay, let's try one more. I cannot stress enough that just because you have a row of zeros, you will have a dependent system. That is not the case. That is not the case. Suppose you were asked to solve this. X plus 2y plus z is equal to 10, and x plus y plus z is equal to 8. Well, when you make the matrix, remember there's a 1, a 1, a 1, a 1, and a 1 over here. So you have 1s for the first column, 2, 1 for the second, first column, second column, then another column of 1s for the third, and then 10, 8. We have our non-zero entry there, which is good. I want to get that to be 0. But before we even do this, again, don't count the right column. There are 3 columns, 1 for each variable. There are 3 variables, but maybe we'll end up with 2 rows when we reduce it, 2 rows that aren't all zeros. Or maybe we'll just have 1 row, but we won't have 3 rows. You never gain another row. In fact, you never lose rows. They just might all become zeros. 1 or 2 or 3 rows or more might become all row or zeros. But you still are going to have 2 rows. You'll never have 3 rows. Right, since both of these entries are 1, we just do row 1 minus row 2. So the first row does not change. And the second row, 1 minus 1 is 0, 2 minus 1 is 1, 1 minus 1 is 0, and 10 minus 8 is 2. Okay. First column, wonderful. First non-zero entry in the first row, what's beneath it is 0. Now we go to the second row. Non-zero entry. First one. I want to get what's above it to be 0. You could do back substitution. That is Gaussian elimination at this point. All right, so I have a 1 here, and I want to get that 2 to be a 0. So I'm going to keep row 1 the same, which will put a 2 right here. Then I'm going to double the second row, because when you double 1, you get 2. And if both of these are 2, subtraction will kill it off. Okay. So what I know is the second row is not changing, but the first row is. Row 1 is 1, 2, 1, 10. And 2 times row 2 is 2 times 0, 2 times 1, 2 times 0, 2 times 2. And I am going to subtract these. 1 minus 0, 2 minus 2 gave me my 0. 1 minus 1, 10 minus 4. I get 1, 0, 1, 6. This matrix is in RREF form. Verify it. Check all the conditions, and you'll see that it's met. Okay. X, Y, and Z. Under X, I have a leading entry. That 1 is the first non-zero entry in that row, in the first row. Under Y, I have a leading entry. In row 2, that 1 is the first non-zero entry. But That's not true in the third column. You may say, yes, it is. There's a 1 here. Fair enough. It's a 1. But it's when it comes to row 1, that 1 is not the first entry that isn't 0. That number is. That tells me that Z is a free variable. Z is equal to R. R is any real number. The second row just tells me y equals 2. Y is 2. No matter what, y is 2. The first row tells me that 1x plus no y's, which I won't write down, plus 1z is equal to 6. Bringing the z over, I get x is equal to 6 minus z. That is, x is equal to 6 minus r. This here is my solution. X is equal to 6 minus r. Y is equal to 2. X is 6 minus r. Y is 6 minus 2. And z is r. Z can be any number you want it to be. If somebody asks you to pick a particular solution, my advice would be, let r equals 0. Z equals 0. Y is always 2. And x is 6 minus 0, or 6. So x is 6, y is 2, and z is 0. That's going to satisfy both equations. Let us verify that. Let us verify this. Who knows? Maybe I'm making this stuff up. X plus 2 times y, which is 2, plus z is 0. Does this equal to 10? Well, this is 4. Yeah, 6 plus 4 is 10. How about that? And the next equation is even easier. It says x plus y plus z. And you add them up. X, y, and z. You should get 8. And yeah, look at this. When I add these three numbers, I get 8. X plus y plus z, it really does equal 8. So that is a particular solution when z is 0. You can let z equal 10. And then y would always be 2 in this case. Y is always 2. It isn't a function of r. It isn't a function of z. It's constantly 2. So to recap everything, if you get a row of zeros to the left of the line and to the right of the line, you don't have 0. You have 7, you have negative 2/3, anything but 0. You're done. There's no solution. The system is said to be inconsistent. If you RREF a matrix, an augmented matrix, and it turns out, and you don't get a row of zeros to the left and non-zero number to the right. That is, if it isn't inconsistent, if the number of variables is bigger than the number of rows that aren't all zeros, it will be dependent. You will get some variables to be free. In fact, it's a little bit abstract, but here goes something. If the number of free variables, will equal to the number of variables minus the number of non-zero rows when in RREF form. So earlier we had 3 variables and we only ended up with 1 row that wasn't all zeros. And yes, we had two free variables. One was called R, and one was called S. Okay, this completes the section on inconsistent and dependent system of equations. Good luck with it.